Hello, YouTube! We've done position graphs, and you guessed it, it's time for velocity graphs next. So, in particular, a lot of the same stuff is off of the position graph actually, where we were focusing on how to figure out, like, how do you read the value? How do you read the slope? What does that actually do? What does that mean? There is going to be an extra layer here, where we're also going to be finding the area, but in particular, the big ones are learning what a velocity graph says about the velocity, and then, and this is the weirder one, learning what a velocity graph says about position, and learning what a velocity graph says about acceleration. Oddly enough, the second one is a lot easier than the first. So, velocity. Just briefly as a reminder, velocity is the direction and rate of travel. So what that means is what the object is doing. If you're looking at an object and you're seeing the thing that's happening to the object, that's going to be velocity. Velocity is what you can see. So if you're looking at a graph, the number on the y-axis is what tells you about the velocity. So if you're looking at a graph and you look at this and you're like, okay, the time is 2, but the velocity is plus 3, that means that the velocity here is positive. A positive velocity means the object is moving forward. If you're looking at it at 7 seconds, then at 7 seconds, our velocity value is 0. Remember, the x exists, but it's the time, not the velocity. So if you're trying to figure out what's happening with the velocity of the object, use the y value because that's actually the velocity. So a positive y value means the object is moving forward. A negative y value means the object is moving backwards. In theory, velocities do have to be continuous because you have to continuously transition between all of them. But for this class, we kind of let them jump around. Something that tends to throw people off about this. This graph is progressively getting more negative the whole time. If this was a position graph, you could look at it and say that the object was moving backwards or stopped for the whole time. However, because this is a velocity graph, the graph is not showing you the object. For position graphs, pretty much the graph is showing you what the object is doing. For velocity graphs, the object is doing what the number of the graph is. The object is not doing what the shape of the graph is. So even though the graph is going down, the object is not moving backwards. So just be careful about that. In particular, one other thing is that because 0 is stopped and plus is forward and minus is backwards, if you go from plus to minus, the way you do that is by crossing the 0 line. So anytime it crosses the 0 line, that means that the object is turning around. So, one other thing about the value for the velocity is that a lot of it's going to come down to fast versus slow. So, if you are far away from 0, that means you have a big number for your velocity. That means the object is moving fast. That can be up high, but it can also be down low. Whereas in the middle, it would be too slow. And I highly doubt, sorry, I don't know if people even do that anymore. So if I ever get completely blown back by my own stupid joke like this, it's because it wasn't at all planned, and I wish I could have gotten myself not to do it. So if you have something that's positive, again, not necessarily bigger than something that's negative. So really be careful. Something that's going up on the graph is not necessarily getting faster, and something that's going down on the graph is not necessarily getting slower. And the big reason for that is really just that up here is fast, down here is fast. So if I go from here to here, I will be going fast at the beginning and fast at the end, and in the middle I will have stopped and gone slow. So was I speeding up? Was I slowing down? Depends on which part you're talking about, but in all of those cases I'm going down on the graph. So again, not really going to work. One other thing about being zero on the zero as stopped, even if it's just barely, barely, barely crossing, or it's only on there for a tiny fraction of a second, that means that for that tiny fraction of a second, the object was stopped. Okay. So what about slope then? Well, acceleration is definitionally the rate of change in velocity, right? So if you have a velocity graph and you find the slope of that velocity graph, that'll give you the instantaneous acceleration of the velocity graph at that point. We're not going to deal with curvy friends in velocity graphs because we only really deal with constant acceleration in AP1. APC is where they have to do that. But not us. So, in particular, if you're asked to find the acceleration of a graph, of a velocity graph, of an object using a velocity graph, the way you would do that is by finding the slope of the velocity graph at the time you're being asked about. So in this case, rise over run to find slope, same way you would do here. In particular, though, if you're being asked to find the instantaneous velocity, insanely easy on a velocity graph, because like the graph just tells you the velocity. So if you're asked to find the velocity at 2 seconds, you can just be like, it's +3 because the y value is +3. Yeah. If you're asked at 6 seconds, you could do basically the same thing and get 0. If you're asked at 13 seconds, you can do again basically the same thing and get -3. Remember, the seconds are on the x-axis. For acceleration, we do actually have to find the slope. So like the slope is 0 here, so that would be the acceleration. The slope is -1.5 here, so that would be the acceleration. Please note, the velocity is positive here, the velocity is negative here. The acceleration can still be negative in both cases because in both cases the velocity is getting more negative. Note that I didn't say getting smaller or bigger because it's actually getting smaller in this case and bigger in this case because it's going from +3 to 0, which means getting smaller, and it's going from 0 to 2 backwards, which is bigger. So that's the thing. So let's actually talk about speeding up versus slowing down. If you have a positive slope on your graph, that means that you have a positive acceleration. If you have a negative slope on your graph, that means you have a negative acceleration. Neither of those inherently means speeding up or slowing down. Hopefully you remember this, but you'll only speed up with a positive acceleration if you're already moving forward. Positive acceleration means that the object is trying to move forward more. The way you get closer to moving forward if you're moving backwards is by slowing down so that you can begin to move forward after that. The way that you move more forward if you're already moving forward is to go faster, do even more of it. Whereas a negative acceleration means you're trying to move more backwards. If you're moving forward, that'll mean slowing down and stopping so that you can move backwards. If you're moving backwards, that means moving even more backwards so you can, again, move even more backwards. If the slope is 0, that does mean that the acceleration is 0. That means that the velocity is constant. For any of these things on the graph, if the thing that's being graphed is constant, it means that you have a flat line. Quick thing from here, stopped means the position is constant. So a constant position means it's on the 0 line. A constant position on the graph of velocity does not mean that the object's position is constant. So something that gets a little weird here is that some of these words, vocab words like position or speed, are words that people might try to use to describe a graph. Just be careful with that, because if you start thinking with those words, you might accidentally mix them up with the vocab words and describe what's happening in the situation incorrectly. So, in particular, 0 is the slowest you can go, right? You're not moving. So, if your velocity is getting closer to 0, either by doing this friend or by doing this friend, that means that you're slowing down. If your velocity is getting further from 0, either by doing something like this or something like this, that means that something like this, that means that the object is speeding up. So if you then want to find, okay, so segueing into something pretty different. if you're trying to find the displacement or the total distance traveled off of a velocity graph, because the y value shows you how much you would change in a full second, and because the x-axis gives you time, what you can do, this makes it really easy to figure out the displacement if it's constant. So if you have a constant velocity like this in blue, what you would do to find the displacement is you'd be like, okay, well, the velocity is plus 3, and for this whole second, that velocity was plus 3. So if I take this chunk right here of 1 second, and I multiply that 3 by 1 second, that will give me 3 meters. So if I take the 3 meters per second, and I multiply it by the 1 second, that gives me that this whole thing is 3 meters. And that's actually really interesting geometrically, because that's the area between the 0 line and the actual graph. Well, what if it's not for a full second? What if it's only for half a second? Well, we can take that same concept and it still works no matter how long it is, as long as we have a constant velocity. Because if we have a constant velocity and it's going for half a second, well, then our time would only be half a second, a little smaller. But our velocity would still be 3 the whole time, so we could still do the 3 times the 0.5, and that would give us that we went 1.5 meters in that time. Okay, great. Where it gets weird, and this is technically calculus, is what if it's not a constant velocity? And the answer is, well, if it's not a constant velocity, if we zoom in enough on this graph, it is really close to being a constant velocity here. So for this tiny little sliver of, let's say, 0.01 seconds, it is basically going plus 3. So what I can do is take this tiny little sliver and multiply it by the time to get the tiny, tiny, tiny amount of distance we travel in that time. Well, if I do that for this little sliver, and 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 we just keep doing that, what we've done is we've built up this thing that mathematically is accidentally the same as just the area of that triangle. And this is the basis of calculus, or one of the bases of calculus. And so what we can do, generally speaking, is that if we have any graph of anything, if the rate of change is a significant thing, taking the slope will give you the rate of change. If you look in the equation for those two things, the x and the y will be divided. So like if you look at the equation for velocity in terms of position, it's position over time. This division symbol means that if you have a position graph and a time graph, dividing the two, finding the slope, gives you the velocity. But if we look at the equation for position in terms of velocity, it's a little different. Position in terms of velocity is equal to velocity times time. Because the two things we're graphing are multiplied, that means we're going to need to find an area. And hopefully this will make more sense after we do some examples, but just to start with. This is going to hold for every single equation that we do where we're going to wind up graphing it. In particular, the ones that are of note. Force versus time will give you impulse, and force versus distance will give you work. And that's going to be really big way later on. So let's actually do some examples so that hopefully this makes a little bit more sense. So in particular, if we look at the graph, if I use the area for a rectangle to get this first section, and my face is like ever so slightly in the way of a little bit of information, so I'm just going to shoosh that down a bit. All right. So if we look at this section, Um, sorry. So if we look at this section, then this section, the base of it is going to be the amount of time that it goes for, which is 3 seconds, right? Keep track of that base because that's going to be what helps you actually make sure you're doing the correct area. There are a lot of really common mistakes that come in here. After we learn how to do it correctly, I'm going to really quickly talk about some pitfalls you should avoid, which is 50-50 on whether or not I'm supposed to do that, because if I don't ever say it, you might not even think to do it, but oh well. But also enough people make the mistake that I think it's worth it. My height for this one is that to get from this base to the actual graph, I have to go up by 3. This is a rectangle. The area for rectangles is base times height. So I can do the base of the height of 3 meters per second times the base of 3 seconds, and that'll give me that this area is 9 meters. So I can take that plus 9 meters, and that will be the displacement for these 3 seconds. For this next one, it's a triangle, so our area function is going to be 1/2 base times height. The fact that the line is going down does not matter for the plus or the minus. This means that the acceleration is negative, but accelerating backwards doesn't mean you're moving backwards. It means you are trying to move backwards, in this case, while moving forwards. Because this is above the line, our velocity here is plus 3, our velocity here is plus 2, our velocity here is plus 1, and our velocity here is 0. The entire time our velocity has been positive, which means the entire time the object is moving forward. So when we go to find our displacement, this one will also be positive. Again, we find the area, so we take that 2 as our base, we take that 3 as our height, and we do the triangle formula, so 1/2 times 3, the height, times the base, 1/2 base height. The order of the multiplication doesn't matter, and that gives us plus 3. There's no area for this part because it's on the 0 line, so it doesn't move, so nothing. If we look at this next section, our base is 2 again, but our height is such that we go down by 2. This matters because this whole time our velocity is 0, then -1, then -2. Our velocity is negative for all of this, which means we're moving backwards for all of it. So we've got -2 as our height. 1/2 times -2 for our height gives us -1, times 2 gives us -2 for our area, so the displacement for this section of the graph is -2. Real quick, just because it occurred to me that it might be a question, if you're wondering about like, well, what do I do for parts where I only want a section of the shape? Just use the base for the section of that shape, or make a new shape that's a subsection of that shape. So if you wanted to know the displacement for the first 2 seconds, you would only use this part of the triangle or rectangle instead of using the whole thing. If we keep going over here, same process. This one is below the line, and the velocity is negative, so the displacement winds up being negative. Velocity is negative because it's literally just -4 this whole time. So -4 times the 2 seconds gives us an area of -8, so our displacement for that section is -8. For this next bit, which our base has a section of 2, we are below the line by 4, but it's not actually just a rectangle, it's not actually just a triangle, it's a triangle stacked below a rectangle. So what I have to do is take this and be like, all right, well, this rectangle has a base of 2, this rectangle has a height of 4. When I find that 2. When I find that area, it's 2 by 2, which gives us -4 because it's below the line. For the triangle, the base of just the triangle in particular is 2. The height of just the triangle part in particular is 2 below the base of the triangle, and so that's -2. The direction that you shade should always be so that it's shading from the line that is the graph to the 0 line. Once you've got those, you can use those to find average speed or average velocity. So average speed and average velocity are not just eyeball roughly where it is in the middle. It's find all the areas, add up all the areas, divide by the total time. Something that's interesting about this, which is the mean value theory. No, it's not. No, it's not. Something that's interesting about this is that if you find that average speed or average velocity, what that will be the same as is if you replaced the whole thing. We've got -6 in total, so we need to replace the whole thing with a rectangle that gives you the same end result as far as the area is concerned, which would be a very close to 0 rectangle below the line. This rectangle has the same area as all these shapes, and that's what gives you the average velocity. The average speed would be much higher for this one. There might actually be a slide where we find it. So, to find our total distance traveled from 0 to 5 seconds, all we have to do is take the stuff from 0 seconds to 5 seconds, which would be this stuff. We've got our area of +9, we've got our area of +3, and so we'll get 12 for our total distance traveled. For our displacement, we keep the signs and it's +12. Even though the velocity went down by 3, the change in velocity was -3, the change in position is going to be +12, because this is not a graph that directly shows its position. We have to do that area stuff. For B, if we want to find the total distance traveled in time from 0 to 14, we add all of our stuff together. So for our total distance traveled, it's all positive. We don't care whether or not it was forward or backwards. We've got the +9, +3, +2, +8, +6, which gives us 28. I hope I calculated it correctly before. Let me double check. 12 plus 2 is 14, plus 2 is 22, plus 6 is 28. Great. For our displacement, we've got +9 plus 3, 12, -2, 10, -8, 2, -6, -4, which I did wrong on the thing, and then just it's hard to change. So that gives us our final displacement for this whole thing of -4. So then, when we're trying to find our average speed and average velocity, we can take those total distance traveled, take those displacements, just like we used to, and divide that by the time. There is not a shortcut just because this is a velocity graph. In fact, it's a little longer because it's really hard to find displacement and total distance traveled. In this case, it'd be the 24 over the 14, or 2, or the -4 over the 14, which would give us -2 over 7, which you could get a decimal of, and that would be fine as well. So that's all the stuff we have to do with velocity graphs. Thanks. Bye, YouTube.